Hello everyone. Today we're going to be going through a quick crash course on probability based on the VCE Methods study design. Alrighty, let's begin. So first of all, what we need to understand is the language that we use in probability. So sometimes you may see an S written in your textbooks. This simply stands for the sample space. Your sample space is the set of all possible outcomes of an experiment. So, for example, if we're talking about rolling a die, then our sample space would be all of the numbers that we could possibly get when we roll a six-sided die. So that would be 1, 2, 3, 4, 5, and 6. Similarly, if we were flipping a coin, our sample space would be the set of all of our possible outcomes. So our possible outcomes when we're tossing a coin would be that we either get heads or we get tails. So our sample space in this case would be heads or tails. Now, say that we've rolled our die now and we end up getting a 5. We roll a 5 when we roll our six-sided die. In this case, we call this outcome an event. So our event here would be rolling a 5. This can be denoted by an A sometimes, and we can write our event as A equals 5. Now, when it comes to calculating probabilities of certain events, the simplest way that we get to do this is by determining the probability of an outcome or an event A occurring. So our probability of A occurring would be equal to the number of outcomes in our event A. So our number of outcomes in our event A, so that's only one in our case, one number, 5, and the total number of outcomes within our sample space. So over here, we've got 1, 2, 3, 4, 5, 6 different outcomes within our sample space. So our probability of event A being rolling a 5, would be equal to 1 over 6. If our event A was actually us rolling either a 5 or a 6, in this case, our probability of event A would be equal to the number of outcomes in A. So over here, we've got 2 outcomes in A. We've got our 5 and our 6, all divided by our total number of outcomes in S. Remembering that our sample space, S, had 6 different outcomes. So in this case, our probability of event A would be 2 over 6. So probability of event A can be simplified and written as 1 over 3. Alrighty, this is some very, very basic terminology that we just had to cover before we delve into anything deeper. Now, there are a few probability rules that we should be aware of before we keep going. The first one that we're going to start with is our complement rule. Our complement rule simply states that the probability that an event A does not occur, so this is denoted by PA dash, so this is the probability that an event A does not occur. So the probability that something won't occur would simply be equal to 1 minus the probability that event A does occur. And this logically makes sense, right? If we flip a coin and get either heads or tails, our probability of getting a head would be 0.5, and our probability of getting a tail would also be 0.5. Our probability of not getting a head would therefore also be 0.5, and this can be determined by going 1 minus 0.5, which was the probability of getting a head. If we use our rolling a dice example, in that case, our probability of rolling a 6 would equal 1 over 6. Our probability of not rolling a 6 would therefore be 1 minus 1 over 6, which can be written as 5 over 6. So, a very simple rule, but a very important one that will come up again. Our second rule that we will be going through is our addition rule. Our addition rule. Now, before we begin explaining this, let's draw up a Venn diagram. Our addition rule is often used to determine the probability of 2 events occurring. So we can either have event A occur, or event B occur, or both events A and B occur. Now, our addition rule helps us determine the probability of event A or B occurring. So what's the probability that we have event A occur or event B occur? And this or is denoted by this little U type of symbol over here. So this means or. So we are determining the probability that we have either event A occurring or event B occurring. Now, this might seem very simple upon first glance, probability of A occurring or B occurring. So you might be inclined to write, well, probability of A occurring would just be probability of A, and the probability of B occurring would just be the probability of B over here. However, if we look at our Venn diagram, our probability of A encompasses both A and B occurring as well. So it encompasses this region, this overlapping region as well. And our probability of B occurring also encompasses that overlapping region. So what this means is that we've accounted for this overlapping region in the middle twice. What we want to do is ensure that we only account for it once. The way that we can adjust for this is by simply minusing one time that we added this probability of both A and B occurring. So when we say and, it's denoted by this upside down U symbol. So this means and. So once again, when we take the probability of A, we account for this section in the middle already. When we take the probability of B, we're accounting for this region again. So to get rid of this double count, we minus the probability of both A and B occurring together. Now, events aren't always overlapping. These non-overlapping events are what we call mutually exclusive. For example, two mutually exclusive events may be Taylor Swift performing in Melbourne and Taylor Swift performing in Brisbane. Both things can simply not happen at the exact same time. So performing in Melbourne and performing in Brisbane can be considered mutually exclusive events because there is a zero probability of both of these happening at the same time. So when we draw this in our Venn diagram, these two events are drawn separately. Now, what does this mean for our addition rule? Well, remember that our addition rule previously stated that the probability of A or B occurring is equal to the probability of A plus the probability of B and minus the probability of both A and B occurring. So minusing that double count of the overlapping events. However, since these two events are mutually exclusive, you cannot have both of them occur at the same time. So this probability is equal to 0. So for mutually exclusive events, our addition rule changes to the probability of A or B simply being equal to the probability of A plus the probability of B. So this event plus this event, and we don't have to account for any double counting when we take the overlap, since there is no overlap in mutually exclusive events. Now, let's go through an example where we apply the addition rule. Let's first define our events A and B. Let's make event A be us rolling any even numbers when we roll a 6-sided die. So our even numbers when we roll a 6-sided die would be 2, 4, and 6. Our event B, let's define that as us rolling any number less than 4. So any number less than 4 when rolling a 6-sided die would be either 1, 2, or 3. Now, if we determine the probability of both A or B occurring, so what this means is the probability that we either roll an even number or the probability that we roll a number less than 4. Now, we can apply the addition rule, which tells us that the probability of A plus the probability of B minus the probability of A and B would give us the probability of both events occurring or either event occurring. If we look at this logically, we can figure out the probability of A. Our probability of A would be equal to the number of outcomes in this event. So that's 3. We've got 3 different outcomes all over our number of outcomes within our sample space, remembering that when we roll a six-sided die, our sample space has 6 different outcomes. So 1, 2, 3, 4, 5, or 6. So that becomes 3 over 6. Same thing over here. Our probability of B would be the number of outcomes in this event. So that's 3 divided by the number of outcomes in our sample space, which would be 6. These can be written as 1 over 2 if we simplify the fraction. Okay, so now we're left with the probability of A being a half plus the probability of B being a half as well. Now, how do we determine the probability of A and B occurring? So this is an event that fits into both of these categories of rolling an even number and a number which is less than 4. Again, looking at this intuitively, we should know that the only even number less than 4 would be 2. And this 2 is found in both of these events. So the probability of A and B occurring can be written as the probability of us rolling a 2. The probability of rolling a 2 would simply be 1 over 6, right? Because our outcome here, we've only got one outcome, rolling a 2. And the number of outcomes in our sample space is still 6. So that becomes 1 over 6. Our probability of both A and B occurring would be equal to 1 over 6. So we're going to minus 1 over 6 from this equation. If we go and simplify this, it should give us 5 over 6 as our final answer. So the probability of A or B occurring would be 5 over 6. Once again, this makes logical sense. The probability of A or B occurring simply refers to the probability of us either rolling a 2, a 4, a 6, a 1, a 2, which we already accounted for, or a 3. So the probability of us rolling any of these 5 different numbers would simply be 5 over 6. Though we can use this intuitive approach to answer this type of question, for more complicated examples, it's always best to use the addition rule over here. Okay, let's move on to our conditional probability rule. So conditional probability is basically used to determine the probability of a particular event occurring given that something else has already occurred. So for example, if we go back to our Taylor Swift example, what is the probability that Taylor performs in Melbourne given that she's already in Australia? These two events are related to one another, so we should be able to use conditional probability for this. To illustrate this concept, let's use a deck of cards. Let's define event A as being drawing a king. Our probability of drawing a king would be our 4 kings that are found in our deck of cards, all over the 52 cards in a deck. If we define event B as the card being a face card, and in case you don't know, a face card is either a jack, a queen, or a king. So the probability that a card is either a jack, a king, or a queen would be 4 times 3. So 4 jacks, 4 queens, 4 kings. So 4 times 3, all over the 52 cards in our deck. So this can be written as 12 over 52. Okay. If we're asking ourselves, what is the probability that we pick up a king, so event A, given that we've already picked up a card that's a face card, so given that event B has already occurred. Note that this line over here is how we mathematically denote given. So what is the probability that event A occurs given that event B has already occurred? So what we're asking ourselves here is, what's the probability that if I've picked up one of these 12 face cards, that one of these 12 face cards happens to be a king? Well, we'd have to make our denominator be the probability of B first. So first of all, we'd have to have picked up one of these 12 cards. The probability over here is out of these 12 cards, right? So what is the probability that we pick up a king, or one of these 12 cards happens to be a king? So we need to account for both the king part of the question now and our 12 face cards part of the question. So our numerator would be the outcome that fits into both event A and event B. So the probability that A and B has occurred. Now, if we look at this logically, our probability of an overlap between event A and event B would actually be 4 over 52. This is because all of our kings are actually face cards. So the probability of us picking up a king, which is also a face card, would be 4 over 52 because all kings are face cards. And we divide this by the probability of event B occurring, which we already determined to be 12 over 52. Okay, a little bit of math here. If you struggle to divide fractions like these, I highly recommend that you split it up. So we are going to write this as 4 over 52 divided by 12 over 52. Going back to our year 4 math, what we do when we're dividing fractions is we turn this division sign into a multiply and we flip our second fraction. So that becomes 52 over 12. Now we multiply our numerators and we multiply our denominators to get our answer. Before we do that, we can also simplify diagonally or vertically over here. So these two 52s cancel out to a 1, and this 4 can cancel out to a 1, and this 12 can cancel out to a 3. So dividing 4 by 4 gives us 1, and dividing 12 by 4 gives us 3. Okay, lovely. So now we're left with 1 times 1 in our numerator, that's 1, and 1 times 3 in our denominator, so that's over 3. So our probability of event A occurring, given that event B has already occurred, would be 1 over 3. So the probability that we pick up a face card that happens to be a king would therefore be 1 over 3. Once again, we did just use our conditional probability rule, but we can also look at this intuitively. The probability of one of our face cards, so we've got 12 face cards in a deck, being a king would be 4 over 12, which also simplifies to 1 over 3. The 4, because we've got 4 kings in a deck, and because all of these kings are face card, we can take it as our numerator. So out of the 12 cards that we could possibly pick up, only 4 of them are a king. So 4 over 12, that's 1 over 3. Once again, you can look at some examples intuitively, but for more complicated examples with more complicated events and sample spaces, it is best to use our conditional probability rule, which is the probability that of A occurring given that B has occurred equals the probability of A and B occurring divided by the probability of B. Now, under the conditional probability rule, we also have to consider when two events are independent. An event is known to be independent if the occurrence of one event doesn't actually affect the probability of another. So, for example, the probability of me studying today does not affect the probability that you will study today. In this case, our probability of both of us studying at the same time, so event A being me studying and event B being you studying, would be considered independent events. So the probability of both of us studying at the same time would not be influenced by the other. Our decisions made are independent. In this case, the probability of both of these events, so both of us studying at the same time, would simply be equal to the probability of me studying times the probability of you studying. So if we substitute this new discovery into our conditional probability rule, so the probability of me studying, given that you have already studied, equals the probability of A and B over the probability of B. So the probability that both of us study over the probability of you studying. So if we make this substitution, where the probability of A and B occurring simply equals the probability of A times the probability of B, so if we put that in there, this would give us P of A times probability of B, all divided by the probability of B. Over here, we can see that these two probabilities cancel out. So our probability of A, given that B has already occurred, would simply equal the probability of A. Again, we can look at this rule intuitively. The probability that I study, given that you are also studying, if these two events are independent, then the probability of me studying, given that you've studied, should just be the probability of me studying, because your actions don't affect my actions. This is why these two events are known to be independent. Now, in terms of the question should always define when two events are independent. Okay, now that we've got all of the easy stuff out of the way, let's move on to our random variables. So what we mean when we refer to random variables is basically a function that assigns a numerical value to each outcome in a sample space. Now, there are two types of random variables. There are discrete random variables and there are continuous random variables. So remembering that we're assigning a numerical value to each outcome over here, not a probability. So an outcome might be tossing a coin and getting heads. In this case, if we flip the coin 5 times, we can either get a heads none of the time, so we only get tails. We can get it once, we can get it twice, 3 times, 4 times, or 5 times. The reason that we refer to this as a discrete random variable is because we can only have one of these outcomes occurring. Only one of these outcomes occurring. These are discrete numbers. In contrast, continuous random variables can take on any value over an interval. So for example, if we're determining the probability that the person walking down the street has a height of 1.52 meters. In this case, our variables are continuous because somebody's height can be either 1.52 meters or it can be 1.53. It could be 1.532 meters. Under our continuous random variables, our outcome can take on any value over a large interval. So for humans, we could either start from 50 centimeters to 2 meters. So over 50 to 2 centimeters, humans can fall anywhere within this category. As mentioned before, contrastingly, the number of times that we roll our heads can only be 0, 1, 2, 3, 4, or 5 times. We cannot toss a coin and get heads 1.5 times, now can we? So this is not considered to be a continuous random variable. It is a discrete random variable. Now, this is very important to consider when we start looking at our discrete probability distributions. So discrete probability distributions. What we normally use is a probability mass function, which gives the probability that a discrete random variable equals a specific value. So our discrete random variable here, so our probability mass function, will give us a probability that a random variable, a discrete random variable x, so x is our discrete random variable. So our discrete random variable x is equal to a particular value or a particular quantifiable value x. So for example, we defined our discrete random variable example as tossing a coin, so let's stick with that. So our probability mass function will give us the probability that a discrete random variable, so the probability of rolling a head, will equal one of these values. So we either get a head 0 times, we get a head 1 time, we get a head 2 times, 3 times, 4 times, 5 times. You get the idea. So once again, our probability mass function gives us the probability that a discrete random variable, keyword here, discrete random variable, x equals a specific value. So our discrete random variable of getting a head in a coin toss could equal 0, 1, 2, 3, 4, or 5 if we're tossing it 5 times. Now let's consider x, our discrete random variable, to be the number of heads in 2 coin tosses. So that's our x. So our probability mass function will tell us the probability that the number of heads in 2 coin tosses equals either 0, or the probability that the number of heads in 2 coin tosses equals 1, or it equals 2. So x over here is the probability that the number of heads in 2 coin tosses equals 0, equals 1, or equals 2. So understanding the notation here is very, very important. Again, we can look at this intuitively. What's the probability that we do 2 coin tosses and we roll a heads once? Intuitively, you should be able to tell this would be 0.5. The probability of us getting heads 0 times or 2 times should be the same, and we know that the probability of each of these discrete random variables should add up to 1. So this should equal 0.25, and this would equal 0.25 as well. So they're the same, and all 3 of these add up to 1. Now that we understand the concepts behind our probability mass function, we can move on to learning how to determine our expected value. Our expected value is simply asking us, what is the expected number of heads that we should be able to get in this situation? So if we take these probabilities, our expected value is simply determined by multiplying our outcomes, so 0, 1, or 2, by their respective probabilities. So if we determine the expected value of the number of heads that we get in a 2 coin toss, then this would equal our first outcome, so 0 times, we get heads 0 times its probability, so 0.25, plus 1 times 0.5, plus 2 times 0.25. If we add these together, the expected number of heads that we get in a 2 coin toss should equal, so that's 0, this is a half, and this is a half as well. So our expected value of the number of heads that we get in a 2 coin toss should equal 1. So we should expect to get 1 heads in our 2 coin toss. We can also apply this expected value to rolling a die. So remembering that we're dealing with discrete random variables at the moment, and we're defining our discrete random variable x as the number that a die rolls. Remembering that this is still discrete because our outcomes can either be 1, 2, 3, 4, 5, or 6. We cannot have an outcome of something like 1.5. That is not possible, therefore this is not a continuous random variable, it is a discrete random variable. The probability that we get either one of these, so the probability of x, the number our die rolls, being 1, would simply be equal to 1 over 6. Same thing for each of these other numbers. So p, x equal 2, would be 1 over 6. 3 would also be 1 over 6. 4, 1 over 6. 5 would equal 1 over 6. And 6 would equal 1 over 6. So if we determined the expected number, so our expected value of x, we're being asked to determine the expected number that a die rolls. If we use our formula as before, where we multiply the outcome by its respective probability, this should equal 1 times 1 over 6, plus 2 times 1 over 6, plus 3 times 1 over 6, plus 4 times 1 over 6, plus 5 times 1 over 6, plus 6 times 1 over 6. Again, just to make our math a little bit easier, we can factorize out this 1 over 6 from each of these brackets. So that should give us 1 over 6 times 1 plus 2, so the values over here, 1 plus 2 plus 3 plus 4 plus 5 plus 6. So this should equal 1 over 6 times 21. So 21 divided by 6 equals 3.5. So our expected value that a dice will roll, our expected value when we roll a die would be 3.5. Okay. Now, for methods, we also cover something called the binomial distribution. Our binomial distribution simply models the number of successes that we can get for a certain number of independent trials. If we write out our binomial distribution, it looks something like this. So the probability that x equals k, so for example, if we make x the number of heads in 5 coin tosses, so let's make x the number of heads in 5 coin tosses, what is the probability that the number of heads in 5 coin tosses equals k? So k can be anything. So maybe this we can say, what's the probability that the number of heads in 5 coin tosses is 3, for example. So to determine this, we would use our binomial distribution, which is written with this formula. Over here, our k refers to the number of heads, so our number of successes, and our p refers to the probability of us getting success. So the probability of us getting a heads rather than a tails in a coin toss will always be 0.5, right? So this is our p in this situation. This part of our equation actually refers to the combination of choosing 3 successes from a distinct set of 5 successes. So the total number of successes that we could possibly have is 5. That is our n, so our number of trials. and the amount of successes is 3. So this is actually a combination, not a fraction. So we will work through how to calculate these combinations together. So the equation for determining our combination would be n factorial over k factorial times n minus k factorial. So let's apply all of the knowledge that we've got. We know that our k equals 3. We also know that our n, our number of trials, equals 5. We also know that our p, our probability of getting a heads rather than a tails, would be 0.5. So our probability of x, the number of heads in 5 coin tosses, being 3, would equal to the combination of n, which is 5, and k, which is 3, times p, which is 0.5, to the power of k, which is 3, times 1 minus p, so 1 minus 0.5, to the power of n minus k. So n minus k would be 5 minus 3 over here. If we use our combination formula up here and apply it to this 5 and 3, we would get 5 factorial over 3 factorial times 5 minus 3 factorial. The rest of our equation we can also simplify over here. So this would be 0.5 to the power of 3. 1 minus 0.5 is also 0.5, so that's still 0.5 in the brackets. And 5 minus 3 equals 2. So that becomes a 2 now. Okay, so 5 factorial can be written as 5 times 4 times 3 times 2 times 1. Our 3 factorial can be written as 3 times 2 times 1. And 5 minus 3 equals 2. So our 2 factorial can be written as 2 times 1. So I'll just write that as 2 times 1 because this is equal to 2 factorial. Okay, over here we can see that these 3's cancel out, these 2's cancel out, and these 1's cancel out. So if we simplify this, we should get 5 times 4, which is 20, divided by 2 times 1, which is 2, and bringing down the rest of our equation, we get a half to the power of 3 times a half to the power of 2. We can combine these using our index laws, and this becomes a half to the power of 5 times 20 over 2, which can be written as 10. So 10 times a half to the power of 5 would be equal to 10 times 1 to the power of 5, which is just 1, and 2 to the power of 5, which equals 32. So 10 over 32 can be simplified and written as 5 over 16. So the probability that the number of heads in 5 coin tosses is 3 would be equal to 5 over 16. So a lot of arithmetic over here, but the most difficult part would be the combinations, I would say. But if you cancel out terms, you should be able to quickly figure this out. As always, you also do have your calculator to use in the calculator exam. So this should be spitting out the answer for you if you put in your value for P, for N, and for K. Now, up until now, we've just been dealing with discrete random variables. Let's move on to what we do for continuous random variables. So for continuous random variables, we would obviously need a continuous probability distribution. Our probability density function here would then describe the probability of a continuous random variable falling within a particular interval. So the probability that our continuous random variable x falls within the interval of a and b would be given by the area under the graph, so our integral, of a function x. The total area under the curve of this function should always equal 1 because the probabilities of all of our different outcomes should always equal 1. The most well-known continuous probability distribution would be our normal distribution. And this is what we refer to as our typical bell curve that looks something like this. Something like this, only a bit more even than I've drawn it. Over here, our expected value or our mean, for example, if we use height, could be 170 centimeters. Now, before we go any further, let's introduce the concept of variance and standard deviation. Our variance and standard deviation are simply measures of the spread of our function. Our variance is usually calculated by taking our ex squared and minusing our expected value all squared. So ex squared simply means that, as before, when we dealt with our die example, each of our outcomes, x, so our outcomes were either rolling a 1, a 2, a 3, a 4, or a 5. Each of these will be squared when determining ex squared. So again, what we're doing is we're multiplying each outcome by their respective probabilities. So an outcome would be getting a 1. Over here, we are squaring this and multiplying it by 1 over 6. Then we'd add 2. We're going to square it and multiply it by its probability, 1 over 6. And then 3 squared times 1 over 6. And then 4 squared times 1 over 6. 5 squared times 1 over 6. 6 squared times 1 over 6. Once again, if we factor out the 1 over 6, we'd get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. And if we simplify this, we should get 91 over 6. From our previous working out, we determined that our expected value, so our E of x, was 3.5. And so to determine the variance, we would take the variance of x, take our ex squared, which we figured out to be 91 over 6. As a decimal, this can be written as roughly 15.17, and we'll minus our expected value squared. So our expected value was 3.5 squared. Once again, if we simplify this, we should get 2.92 as our answer. So the variance of a fair die roll is approximately 2.92. So this is just describing the spread of our function. Now, the reason that we normally use standard deviation rather than variance is because the units of standard deviation are in the same units as our original function. So for example, if we look at this height graph, if we determine the variance, the units of variance would not be centimeters. So to find a measure of spread, which is in the same units as height, so which is also in centimeters, we use our standard deviation. And your standard deviation is simply the square root of your variance. So the units of your standard deviation will always be the same as the units that you've got in your distribution. So over here in this example, it would be in centimeters. The units of your standard deviation in this case would be centimeters as well. So it provides a better measurement of the spread of this graph. So this graph could have been spread out a little bit more if I wanted to draw it that way. Standard deviation is also denoted by this sign sometimes. That is our standard deviation. Okay, now let's go back to our normal curve and apply our new knowledge about standard deviations. Here is our bell curve. Here is our mean, our expected value, which we said was 170 centimeters. If we determine our standard deviation to be 10 centimeters, so standard deviation equals 10 centimeters, also this should be given to you in the question, we can apply this knowledge to determine the probability that a number falls within a range. So the probability that a person is between 160 and 180 centimeters, we could determine by taking the area under the graph of this curve. However, we have certain rules that help us skip this step. This rule is known as our 68, 95, 99.7 rule. What this means is that if we are measuring the probability of something falling within one standard deviation of the mean. So over here, this is one standard deviation of the mean on either side because it's plus or minus 10, right? So 170 minus 10 would be 160, 170 plus 10 would be 180. So if something falls between 160 and 180, so within one standard deviation of the mean, its probability will always equal 68% or 0.68. If something falls between two standard deviations of the mean, so over here, this would be 150, so that's within two standard deviations, so we're going plus or minus 20 from the mean, so that's two standard deviations. Two standard deviations would be 20 centimeters, so 150 over here and 190 over here. So the probability that anybody falls between the heights of 150 and 190 would always equal 95. The probability that somebody falls within three standard deviations of the mean, so that would become plus or minus 30. So there's another 10 here. Three standard deviations would be 3 times 10, so that's 30. So 170 minus 30 would be 140, and 170 plus 30 would be 200. So the probability that somebody falls between 140 centimeters and 200 centimeters would actually equal 99.7%. So this is your 68, 95, 99.7 rule. So it simply states, so 68, 95, 99.7 rule simply states that within one standard deviation of the mean, our probability would be 68%. Within two standard deviations of the mean, our probability would be 95%. Within three standard deviations of the mean, our probability would be 99.7%. Now, we don't always like using a bell curve which has different means and different standard deviations. So we don't always like having a mean of 170. In fact, when we're dealing with probability, we always prefer to have our mean equal 0. So in order to convert this 170 into a 0, we try to standardize our graph. So when we're standardizing our graph, we are just trying to make our mean, so this is the symbol that denotes mean, equal 0, and we're trying to make our standard deviation equal 1. Now we can do this for any number that falls within this range. So we can standardize any number over here. But just to illustrate the concept, let's standardize our 160 and 180 and see whether it gives us a standard deviation of 1 and a mean of 0. So our equation to standardize a value x, so our height x, would be x minus the mean divided by the graph's current standard deviation. If we do this for 160, so we take 160, which we know is within one standard deviation of the mean, then we take 160 minus mu, so the mean of our graph at the moment, 170, divided by our current standard deviation of 10. So if we standardize this value, so that's z, this should give us negative 10 divided by 10, which equals negative 1. Remembering that now that we've standardized this graph, it is most ideal because this means that our 160 has now been converted to negative 1, our mean has been converted to 0, and let's try it with 180. This should be converted to 1, so within one standard deviation. So before it was within one standard deviation, even now it's within one standard deviation, only we want our standard deviation to be 1 instead of 10. So let's try that with 180. So standardizing, we take our x, 180, minus our mean of our original graph, 170, divided by our standard deviation of our original graph, which was 10. This should give us 10 over 10, which equals 1. So our 180 now becomes a 1. Now, standardizing is useful when we're trying to compare two different bell curves with two different means and two different standard deviations. So an example question could be something like this. So say that we've got Alice and she scored 78 on a math test. So she scored 78 on a math test. Now this math test had a mean of 70 and a standard deviation of 5. Now this is for maths. Say that Bob was in a science class. Say that he scored 82 on his science test. However, in this class, our mean was 75 and our standard deviation was actually 7. If I ask you the question, who performed better, you may want to say Bob, right? Because he got the highest percentage score. But it wouldn't be fair to judge them this way when the mean score in this class was actually higher than the mean score in Alice's class. So this is why we standardize both of these examples. So if we standardize this 78%, so standardizing would take our x over here, which is 78%. We take 78 minus our mu. So remembering x minus mu, x minus our mean over our current standard deviation would standardize our equation. So we take that, x equals 78, our mean equals 70, and our standard deviation equals 5. So over here, our standardized value would be equal to 8 over 5, which equals 1.6. For Bob's science class, if we also standardize this one, we'd standardize our x, our value, which is 82. That's 82 minus mu, which is 75, divided by our standard deviation, which is 7. So z would then equal 7 over 7, which equals 1. So what this means, that on a standardized bell curve, so on a standardized bell curve where our mean is 0 and our standard deviation is 1, Bob actually scored over here with a standardized score of 1, and Alice actually scored up here at 1.6. Now, if you ask the question, who scored better, it's actually Alice who scored better because she sits higher on this standardized bell curve. So this is Alice's score and this is Bob's score. So Alice is actually the one who performed better and not Bob. So a higher Z score, a higher standardized score, means that the score is further above the mean in terms of standard deviations. So Alice's Z score is 1.6 and Bob's Z score is 1. So Alice had the better score. She performed better relative to her class because her score was 1.6 standard deviations above the mean compared to Bob's 1.0 standard deviation above the mean. So standardizing basically enables fair comparison across different tests or distributions by putting scores on the exact same scale. One last thing to cover would be our cumulative distribution function. So that's your CDF, your cumulative distribution function. Your CDF, so your function, is used to give the probability that a random variable is less than or equal to x. So this can be any random variable. It can be continuous, it can be discrete, any random variable. So it gives us the probability that something is less than or equal to x. You can also use it for less than x, more than or equal to x as well, or even within a range. So for example, if we take our discrete random variables, let's do the number of heads in a 2-coin toss. Our probability that we get number of heads that are less than or equal to 1 would equal our probability of getting 0 and our probability of getting 1. So this would equal 0.25 plus 0.5. So we determined these values, these probabilities before. This would equal 0.75. So the probability of getting something that's less than or equal to 1, so getting number of heads in a 2-coin toss that are less than or equal to 1 would be 0.75. For our continuous variables, so if we had x is less than or equal to, say, negative 0.5, this would simply be the area under the graph less than this value. So the probability of this test score, this outcome having a z-score of less than or equal to 0.5 would simply be the area under the graph below negative 0.5. Our probability that somebody's test score had a z-score of less than or equal to 1 would therefore be the area under the graph below 1. So all of this region for a continuous random variable. So these are known as our CDFs, our cumulative distribution functions. Alrighty, as always, let me know if you have any questions. Otherwise, I will see you next time. Hopefully this is helpful going into your SACs or as an intro to probability before you step into your first probability math class this year. Note that in this video, we actually haven't covered how to find the expected value, variance, or standard deviation of continuous random variables. I will make a separate video on this, but yes, just making note that every example that we did in this video where we determined the expected value, the standard deviation, they were all discrete random variables. I have also made note of this in the chapter labels.